our theory T is sound. Okay. May I erase this condition? Okay. So what we do is, when we formulate T in this way, T is T0 plus phi, and phi expresses its own consistency, then the theory must be sound. Okay. Assume it is not sound. Assume otherwise. It is only possible if our new axiom phi is false, because all the other axioms are true. This was one of the conditions. Okay, and phi expresses consistency of phi, and this is verifiable in a sound theory, right? So that means that consistency of T is false, or in fact T is inconsistent. So started with the assumption that T was not sound, and further T is inconsistent. Okay, now we proceed as follows. Let P a minimal proof of falsity of the formula 0 is 1 or something like that, depending on what falsity means in our case. It's a T proof of contradiction. So take the minimal proof of contradiction in T. Okay. And let N be the height of this proof, which means that there is a maximum height of all formulas occurring in this proof P. Okay, so that's also a finite number. Then what we have is, for some axiom A occurring in this proof P, it must be false. Right? So P is a proof of contradiction, and contradiction is okay. If all formulas
say it again. So what is the height of P? P is a number or a real proof?
P is in fact a real proof because we are in the standard model.
Okay.
We are in the standard model, so it's both a number and a real proof. And it's the maximal height of formulas occurring in T. So what we have is, then we claim that for some axiom, from that proof, that axiom must actually be false in the model Mn. That's the consequence of this lemma, because otherwise all formulas which are in the standard model transfer to Mn. Which axiom could that be? Of course, the only axiom, the only available axiom is again the same axiom phi, for using the same principle, because T0 has pi 1 of L axiomatization. So all axioms of T0 hold in the standard model, so they hold in Mn. Okay, so then actually since this is only possibly false axiom. Okay, so we obtain that this consistency of T, false, is false in Mn, already in a finite piece of natural numbers, which means that, reading this formula, that there is a P prime such that proof of contradiction in Mn, in T varied in Mn. And the point is that P prime belongs to Mn. Now what we have is that the following thing. P prime is smaller or equal n. Okay? And this is smaller or equal P. And this is smaller than P. And here comes the condition which I did not mention, but it's a kind of natural. You see, the height of a proof is strictly smaller than the Gödel number of that proof. But the height of a proof is sort of a maximal constant occurring smaller than P. So that's a natural assumption. So we have P prime is strictly smaller than P, and we have here T P prime is also valid in the standard model because that formula was delta 0 of L. Right, again, lemma in the other direction strikes. So this is the end of the argument, as you see. The miracle infinite descent, so to say.
Descent?
Yes, but of course we are working with a standard model, so there is no problem of having that argument. Okay, so that's it. So you see that now the only task basically that we have to do is to construct this theory T0. Because we finished the proof. We have a theory T which proves its consistency because it's essentially an axiom of it. And we have proven that this theory is sound. So.
But somehow you have cheated us because you agreed that we need some extra conditions. Okay, I cheated myself maybe, but you agree that we need some extra conditions on T0, but you haven't used any conditions actually.
Well, I have used that T. I have used that T0 has pi1 acceleration.
I mean that's the condition, except those 1, 2, 3, 4, 5.
I have used a fixed point lemma, right?
Okay.
So I used the condition of the fixed point lemma. It is simply, well, the cheating was, it was not the cheating, it was somehow, I made two, let's say, a grand assumption. So validity of fixed point lemma should not be stated as a condition because it's, in fact, it's a thing which should be rather proved from more elementary conditions. If you
Okay. So you actually need only fixed point lemma.
Basically,
I mean,
yes. So together with all the rest,
so
which was
yeah. If everything is right in your proof, then for every t sub 0 satisfying those items,
yes.
Theorem holds.
Yeah, but I think that the main...
There is this minor condition was here. Because
Yeah, I think the main mystery here is that the claim is that you still can have some natural reasonable things provable after you forbid everything increasing, and so you force to allow the finite models.
Yes. So
it's rather strange that you somehow you still make this final model property and still be able to do something. So this is kind of belief which should be justified by long training.
Exactly. So what I would like, I will not be able to prove all these conditions, of course, but I will formulate more explicitly what is T0, and then I will try to somehow wave hands and to explain how to work with T0 to start proving these conditions. So, okay. And in fact, in that part, as I said, I am simplifying Willard a lot because he actually worked with, his system was pretty complicated. So he coded everything using this linear time hierarchy, so to say. So he used some facts from complexity theory quite extensively, etc., etc., complicated things. What I will be presenting is more in the spirit, I would say, of the original Gödel approach with primitive recursive functions. And that's considerably simpler if you think about it. And I think the effect will be the same. So, another remark which I would like to say is that one can actually strengthen this theory T0 by adding more pi1 of L axioms. In fact, as many as we want. For example, we can formulate the theory T1, which will satisfy all the properties which I mentioned for T0, but in addition, it will prove all, for example, pi1 of L consequences of Piano. So, we can construct such an example of a theory which will be, in some sense, in terms of proving pi1 facts, will be as strong as Piano. But not in terms of proving facts about functions which are growing. The existence of successor will be still beyond the issue. Okay, now we turn to the definition of T0. Okay, so we start with describing this set of functions L, and they are precisely defined as precisely as primitive recursive functions. This is very strange. So our basic function functions, constants, all constant functions are assumed here for obvious reasons, and instead of successor, we will have a predecessor. X minus 1 source, and predecessor of 0 is 0, as always. And that's more, funnily enough, that's the only change we need. I believe that everything should work with this formulation. Okay, so the schemas defining new functions are composition and recursion, primitive recursion, which is slightly modified from the usual form of primitive recursion, but you will see, I will, let's say f of 0 x is g of x, so and f of 1 x equals h f of n x. The slight difference is this n plus 1 instead of n. So if we just had n here, that would be the literal what is in Mendelssohn's textbook or something like that. Of course, it is equivalent to that formulation. But in our context, we will obtain somewhat more growth if we have n plus 1 here, because inductively one can show that indeed all f non-growth. And of course I have forgotten the projection functions. They are also non-growth, no harm. So composition together with projection allows us to interchange variables in functions and do things like that. And this primitive recursion, as you see, if neither of them, composition of course preserves non-growth character, because sort of f of g of x is more equal than f of maximum x more equal maximum x, right? So, and this schema also produces a non-growth functions, a function if both g and h were non-growth, because Okay, that will be bounded by maximum of nx, and this is maximum of n plus 1x, and that's the explanation why we have n plus 1 here, because otherwise we would have even a function which is decreasing somehow, which is a little bit, maybe that's no harm, I don't know. So, to be honest, I sort of invented this approach approximately 3 days ago, so I haven't yet all the questions answered about this.
Yeah, but these are not the axioms of theory, because
It's not an
plus
axiom
one.
of theory. I'm just describing
external definition of
it's
what
an
class of...
external definition
Yeah,
of functions and their meaning in the standard model. So to say. That will be our approach. And that's the description of the class L. Now, what will be the axioms of our theory?
Not just before the axioms.
Before
For example,
axiom, let's say
a logarithm function. Is
Okay,
in this
what-
class or not?
Yes, yes. The answer is yes. And let me describe a few. Let me start developing, so to say, these functions a little bit. So first, what we should define is, of course, subtraction. That's quite obvious using primitive recursion on y, right? So it's something like x minus 0 is x, and x minus and okay, x minus n is x minus n plus 1, what does it equal? Predecessor x minus n, right? So this is fine. Using predecessor, we can define, for example, inequality. Right? Having inequality, we have equality. So then we define logic, so to say. We define, for example, conditional. And if you look at it, it is essentially also a recursion, right? Because I guess it's clear, right?
Over z, yeah.
Over z, yeah. It's a recursion over z, so it's a 0 case, that's n plus 1 case, and this is also non-gross. Okay, then we can define, for example, inequality, right? When we say, for example, f of x is not 0, that's the same thing as saying that 1 minus f of x is 0, so that's negation, conjunction. Okay, we can define maximum and minimum. Maximum, something like x is small, x, y, right. This is defined using conditional and inequality, right? And of course minimum similarly. And then conjunction, f of x is 0 and g of x is 0 is simply equivalent to maximum of f of x or g of x is 0, right? Well, anyway, we have logic, Boolean logic, and we have bounded quantifiers, right? So we have bounded mu operator as in usual primitive recursive functions. So we bounded mu operator. It's also defined by recursion on A. Since it is bounded, there is no problem of having it in that form. Okay, with respect to how to define logarithm, well, I will define, let's say, function. Okay, I can define addition, multiplication, and logarithm. That's interesting. So graphs of addition, multiplication. After that, everything is more or less clear, because then you can use any of the textbooks which develop this problem. Yeah. So addition, multiplication, and logarithm. So here the trick words which has the following style. Okay. So let's first define sort of bounded successor function. S of ax, which is equals to Sx if Sx is smaller than A and A otherwise. How do we do that?